Let's spend a few more minutes on the traffic control system. Unless the traffic control system is of what I called a smart kind, you will have noticed that it is a system that involves previous timing. It is what I have called a pre-timed system, as contrasted with an online system. Depending on the time of the day, you have a signal cycle operating for a certain period, and the system is turned on and turned off. There are other examples of such systems. One that comes to my mind immediately is that of a robot, a small one, which is, let's say, supposed to do a very simple job of picking up an object of a particular kind, maybe a screw or a cap of a bottle, pick it up from a place where it will be there, lift it and place it at some other place. Maybe the screw is to be inserted into some hole, or the cap is to be placed on a bottle. Not a very difficult job for a robot or an automatic system to do. Pick up something from a place where it is expected to be, known thing, lift it and put it down at some other specified place. Does not require too much of smartness. Now in this case, the movement of the robot arm can be completely predetermined. So the robot arm moves in a particular way, starting from, say, some standard position, goes down to that object, and then if it is holding the object with a pair of pincers, some specific action of the pincers will take place, and the robot arm then will swing around till the object is very close to where it is to be put, and then the pincers will release the object. So the whole thing can be pre-timed, predetermined, or pre-programmed. So there is no feedback being used here. Of course, the robot engineer has done his previous calculations as to how the movements should take place, and somehow he has arranged for those movements to take place as the robot goes on doing its job. But there is nothing online, so to speak. There is a definite sequence of actions, and the robot follows that sequence. Of course, as we can expect, if something goes wrong, then the whole sequence will go, the robot will go through, but it will result in some problems. For example, suppose the object which is to be picked up is missing for some reason. Then what will happen? The pincers will try to close on that object, but will fail to close, and maybe the robot will just swing around and take that object which is not there in its jaws or pincers and put it down, and of course there is no object to put down. So even with such simple robots, there may be some overall supervision required, or some feedback in the form of whether an object has actually been picked up or not may be built in. So once again, as I said earlier, there is hardly any control system which does not use any feedback. One more example of a different kind, and which is in the news nowadays, it has been there for some time, is that of launching of a satellite. That is, involves firing a rocket from ground and taking the satellite up to a particular height or altitude, and then launching the satellite into a suitable orbit. Now in this case, once again, the space agency people do all the calculations previously as to exactly how the rocket engines should be controlled, how the orientation of the rocket should be changed, when the satellite should be released, when the thrusters which the satellite may have to orient it properly should be fired, for how long, and so on. All these things are pre-calculated. But once again, there is usually some feedback on top of it. The space people will check whether things have actually happened the way they were supposed to happen. For example, the orientation of the rocket, the orientation of the spacecraft, and so on. Although they would have done their calculations beforehand, and they are more or less sure that things will go according to their calculations. Still, finally, some element of feedback is necessary, because things can go wrong. So there is this difference between pre-timed, pre-programmed or predetermined control action versus control action which is online, so to speak. That is, what will happen will depend on what has happened actually. The traffic control system was a pre-timed or pre-programmed system, so also the robot doing a very simple job, and the launching of a satellite would also be of the same kind. But if we come to the air conditioner example, there the action is a little different. I mentioned that the air conditioner really does not, the thermostat is the element of the air conditioner which does it. It does not really maintain the temperature absolutely constant. The kind of air conditioner that I talked about, it was necessary that the air conditioner or the air cooler is switched on and switched off. As the temperature outside is high, people have come in, the room is hot, the air conditioner is turned on, the temperature is higher than the desired temperature, so the cooling is kept on. Then the temperature reaches the desired temperature and perhaps goes a little below the desired temperature, the cooling will be turned off. Because of the heat of the people present or changes in outside temperature, perhaps the temperature will start rising once again. And this time, when the temperature exceeds the desired temperature slightly, in our example 27.1 degrees Celsius, the air conditioner will be turned on again. So there is an on and off action which is going to be taking place all the time. However, all this is not predetermined or pre-timed. It is not predetermined that the air cooler or air conditioner will be on, the compressor will be on for 30 minutes and then it will be switched off for 15 minutes and then again switched on for 30 minutes and off for 15 minutes and so on. Unlike the traffic signal cycle, where the signal will be green for 1 minute and then maybe red for the next 3 minutes, then back to green and then red and so on. So the action is not pre-timed. Of course, if one could know beforehand what was likely to happen, for example, if one knew that the outside temperature was going to remain absolutely constant at say 30 degrees Celsius or 35 degrees Celsius, people in the room were going to be there all the time, there was not going to be any heater turned on or any other source of heat. Given such ideal conditions, it would be possible to figure out an on-off cycle, or it would also be possible to select the volume of air which should be circulated or the temperature of the air which is being circulated, so that the room temperature is maintained exactly at the desired value. In our case, it was 27 degrees. But all this is under very ideal situation. The outside temperature remains constant, the inside sources of heat are not changing, and therefore a constant amount of heat removed results in a constant temperature of the room. And if one could know about all this beforehand, if one could pre-calculate everything, then there is no need for feedback. There is no need for a thermostat to check the temperature and then turn the air conditioner on or off. One would have made calculations beforehand, set the desired volume of air to be circulated at a specific temperature, and one would be assured or one would be confident that the desired temperature will be obtained. So this brings us to one of the main reasons for using feedback in a control system, in an automatic control system. When a human being is a part of a control system and is doing the control job, obviously he is looking at things, he is feeling things and so on. So he is serving as the feedback device or feedback element. But in an automatic control system, one will need feedback for reasons of this sort. The system which it is supposed to control, one knows about it fairly well. In fact, you cannot control something if you know very little about that system, or you cannot devise a control system unless you know what that system is like. Take the simple example of a ceiling fan. What kind of a regulator and what design of regulator one should have will depend on the ceiling fan. If it's a small fan, you will require a regulator of a particular rating, because so much current will have to flow in it and not more. Whereas if it's a big fan, an exhaust fan for a big hall, then obviously a current of a different magnitude is involved, and the regulator correspondingly will have to be appropriately selected. So depending on the job, one will have to select the control system. So you have to know what is the application, what is the motor, or what is the oven or tank or whatever it is that you are trying to control. On the basis of that knowledge, you design the control system, make all the calculations. Think of the rocket satellite example. We know what kind of rocket one is going to use, rocket engine, weight, fuel, the rate at which thrust will be produced, and so on and so forth. So obviously we have to know the system before we can control it or devise a control system to control it. But then why is it that one needs feedback? Well, one needs feedback for the reason that although one knows the system to the extent possible, one may not know it to 100% extent. Very often there are things in the system which you cannot determine beforehand very precisely. There are things which might change with ambient conditions. No system is completely isolated so that it is guaranteed to behave exactly the way you expect it to. Take the room air conditioner example. We have control over the room air conditioner, but we have no control over the sunlight, unless you want to design some control over the sunlight. So whether it's going to be cloudy or whether it's going to be very sunny, what is going to be the temperature outside, whether it's going to be 35 degrees Celsius or 30 degrees Celsius, how many people will be in the room, how many lights will be on, maybe some other sources of heat, the cooling capacity of the compressor, all these kinds of things, although you try to find out beforehand as far as possible, everything is not fully known. A general broad term for this could be uncertainty. You are not very sure about the system, or more important than the system, perhaps about the surroundings, about the environment in which the system has to work. A typical example of uncertainty is power supply voltage. In fact, even the existence of a power supply, one may be uncertain. And so we have standby or backups. So in case the power fails, like for example you are watching me on your TV screens, if the power supply goes and you want to continue watching me, you will have to provide some standby power supply. So since the system operates in an environment and the environment is not fully under our control, we cannot be absolutely sure. The system has many components in it. We know, of course, quite a lot about them. One particular component is a resistor, so it has a certain resistance. Another component is a transistor, of a particular type, maybe an integrated circuit, maybe a motor, this, that, and the other. It's true that we do know quite a lot about the components before we put them together, but still there is some uncertainty. For example, resistance or resistor. The design value or the value that hopefully has been used may be known to me. The circuit diagram for the system or device or amplifier, for example, will give me the value of the resistor as, say, 1.5 kilo ohms. But does it mean that the resistance, that particular resistor, is always going to have a resistance of 1.5 kilo ohms, or even at any time? Has someone made absolutely sure that that resistor has resistance of 1.5 kilo ohms, and you mean 1.50000 kilo ohms, not 1501 ohm or 1449 ohms, exactly 1500 ohms. Maybe it was measured to be exactly 1500 ohms or 1.5 kilo ohms, but when the system is actually working, heat is produced. So for all you know, the resistance may increase. In fact, we know that transistor parameters are very sensitive to temperature variation. That's why you provide some kind of a cooling arrangement. So there are many such reasons why you may not know completely, or the previous knowledge that you have about the system that you are trying to control is imperfect. There is uncertainty. When one talks about uncertainty regarding a resistance value and the possibility that the resistance value may change, one talks about parameter uncertainty or lack of complete knowledge about the parameter value, or we do not know precisely what the parameter value is. So this is one kind of uncertainty, parameter uncertainty, or parameter variation because of heating that is occurring or cooling that takes place and so on. The parameter value does not remain what it was, or with repeated operation the parameter values may change. We say that the motor has become weak. Maybe the motor has been used, the blender or the mixer motor has been used for a long time, and so something has happened, and therefore it's not as powerful as it was before. It has become weak. It happens to human beings, it can happen to machines also. Of course, it becomes weak perhaps for a different reason. Perhaps a part of the winding has got burnt out or something like that. Therefore it is not producing as much power as it was producing earlier. So parameter values can change or may not be known exactly. There are some other variables or signals such as the power supply voltage, power supply frequency, maybe temperature of incoming water or pressure, which changes. Sometimes these changes are also referred to as disturbances, for an obvious reason, because they do disturb your calculations. You have made all your calculations, everything was nice, but now this thing comes. Suddenly the voltage has dropped and your system does not work properly. So sometimes they are called disturbances. So there is a difference between a parameter change or the lack of complete knowledge or uncertainty about a parameter value and a disturbance like a sudden increase in temperature, say the sun is coming out of the clouds, or in the case of an aircraft there is some turbulence or there is a sudden gust of air, maybe the weather is stormy, the aircraft is flying through a cloud and whatnot. So in that case one would talk about disturbances. So you have uncertainty, you have disturbances, because of which what you may have pre-calculated, predetermined, may not produce the result that you expect. And so if you want the system to be controlled properly, you would like to see what is actually happening and take any corrective action. If the supply voltage has gone down and because of that some intensity of some light is low or some current is low, then I may intervene if an operator is sitting there and try to adjust things so that the current is brought to the expected value or to the desired value, and so on. So this is the reason for using feedback, that what you expect may not happen, and so one would like to keep watching constantly, monitoring, measure, and then change the course of action or take an appropriate action. Now this is what you can say the thermostat is doing. The thermostat monitors the room temperature, and the moment the room temperature goes above a certain value because of maybe environmental factors or a lot of people coming in and things like that, the thermostat turns on the air conditioner. And after some time the temperature goes down, maybe a lot of air has been circulated or the outside conditions have become cooler, the temperature goes down, the thermostat intervenes again and switches off the air conditioning. So we need this constant watching, monitoring, observing, whatever we want to control, whatever we want to keep constant: room temperature, pressure, supply voltage, frequency, concentration, speed, name anything. Of course, all these are situations which I have called earlier regulator type situation. That is, in this case, some variable or more than one variable is to be maintained or is to be kept constant at some specified or desired values. And one uses the word maintain or kept because usually some action will be required, some intervention will be required as the system proceeds. You cannot simply set it at a pre-calculated value and expect that things will go on without any problem. So these are known as regulator type systems, and in the case of regulator type systems, feedback is required for the reasons that I mentioned. One of the earliest industrial examples of feedback, I don't know whether you have read anything about it or you have heard about it. I mentioned, of course, the ancient tank filling and flushing system, and there is feedback used there, although there is nobody watching, there is no literal measurement being made, but the float valve is an arrangement that provides for the inflow to stop when the water level reaches a certain height, and then when the water level falls below, the flow begins. So that's a very ancient example, but that was not for an industrial application. One of the earliest for the industrial applications was for the control of the steam engine. Before the steam engine was used for locomotives, that is for providing transportation, it was being used basically for grinding of grain for mills, and then subsequently for various other operations. Now the steam engine, of course, uses steam coming from a boiler. The boiler has water in it, it needs a fuel supply. Then there is the wheat which is to be ground, the amount of wheat, the quality of wheat, the condition of the grinder. All of this can result in a situation where the grinding is not proceeding satisfactorily because the steam engine is not producing a proper speed of the shaft of the grinding wheel. So let's say it is desired to keep the speed of the grinding shaft constant in spite of or irrespective of what? Irrespective of maybe the quality of the wheat, maybe the quality of the fuel that is used in the boiler, and things like that. So if a human being were to do it, of course he would see that the speed is falling the grinding wheel is slowing down, and so he would control a valve which will admit more steam into the steam engine. Of course, to produce more steam, you may have to increase the heat given to the boiler, and because the steam is going to be coming off from the boiler in larger quantity, you may have to check the boiler water level and whatnot. So human operator would do the job, and would do the job reasonably well. But as we said earlier, the reliability, the accuracy, these are limitations. So James Watt was one of the earliest of the engineers who looked at this problem and designed what is called the fly ball governor. This is what the fly ball governor looks like. Such governors, of course, you will not find in easily today, simply because steam engines have almost disappeared, and instead of the fly ball governor, one has found out other ways of controlling the speed, or rather monitoring the speed of the engine or of a shaft. In fact, think about this. How is the speed of a shaft today measured or monitored? But James Watt was quite some time ago, more than 200 years ago. So what we can do today was not available at that time. So he devised this mechanical arrangement called the fly ball governor, using the centripetal force kind of action. If the grain was say such that there was less torque required to grind it, so that the grinding wheel would have speeded up, then the two fly balls would fly away with the increased speed. That flying away movement of the fly balls by some linkage led to a valve which controlled the steam flow and which would reduce the flow of the steam. On the other hand, if say there was some problem with the fuel itself, then one would have to modify this a little more, but again the same thing would happen. If the amount of steam that is going is not adequate, then the speed would go down, the fly balls would come closer, and the levers operating would open the valve more, so that more steam would be admitted. This is somewhat similar to our room air conditioner example. The temperature is to be at 27 degrees Celsius, but we find that it's going to oscillate between two limits, 27.1 degrees Celsius and 26.9 degrees Celsius. In the case of the fly ball governor also, such a thing is going to happen. The speed will not be absolutely constant, but the speed will vary between two limits, but the variation can be tolerable. It can be made much less than what it would be without this feedback action. And we'll look at this later on in more detail. This is related to the concept of error, and there are some misconceptions around this concept of error. In your control theory book or control systems book, there will be a long chapter on control system error, types of systems, and so on and so forth. But there is some confusion there, and we'll look at it in detail and try to clarify what exactly one means. So feedback is used because of uncertainty, lack of complete knowledge, disturbances, and so on. For a regulator type system, when something is to be maintained constant, is to remain desired to remain constant, but things may act on it to change it, things which are not known to us, disturbances, changes in parameter values, and so it is necessary not to just make some pre-calculations and get the thing going, not look at it at all, but to keep on looking at it and then make changes that can bring back the desired variable the variable which is to be kept at its desired value closer to the desired value. This is one of the most important reasons for using feedback. There are other effects associated with feedback which unfortunately people confuse with the main reason for using feedback. During admission interviews, when I ask a question, why is feedback used, very often I get the answer to make a system stable, as if a system is unstable to start with and you need feedback to make it stable. Of course, there is going to be a chapter, and therefore we are going to devote quite some time on stability of a system. But in fact, feedback may make a stable system into an unstable system if it is not designed properly. So that's not the reason for using feedback. Of course, feedback may increase or improve the stability of a system. If it does, that's well and good. And if it doesn't, then one has to be careful. But the reason for using feedback is not to make the system stable. In fact, there are hardly any intrinsically unstable control systems. There are. I'm not an aeronautical engineer, but my aerospace or aeronautical friends tell me that an aircraft with its control surfaces for controlling the various motions of the aircraft is what may be called an intrinsically unstable control system. And in fact, if you just go back to our older example of a bicycle, then a bicycle also, one can say, is an intrinsically unstable control system. If you just have a bicycle, say, hold it for some time and then leave it, it's not going to stand there just like that. It's going to fall. And so a human being who is riding the bicycle constantly needs to assess what's going on through what is called the kinesthetic sense and keep on balancing the bicycle. And once in a while something happens and we fail and we fall. So even a bicycle is an unstable system, or what is called maybe a, in case of stability, one talks about various kinds of stability, neutral stability and this, that and the other. So you can think over this example. Whereas similarly any two-wheeler will most likely be an unstable system. It requires a balancing act. But a three-wheeler or a four-wheeler does not suffer from that problem. A motor car driver does not have to balance his car. Of course, when he steers around a curve at high speed, he has to take care. But normally, he does not have to worry about balancing. So to repeat, the main purpose of feedback is not to make a system stable, or the main reason for it is not because the system is unstable, because in very few cases the system will be unstable to start with. The main reason is uncertainty, lack of knowledge, disturbances about which we don't know, parameter variations, and so on and so forth. And so the control system designer has to now think of how this feedback should be used to control the system when such things happen, when there is disturbance, when there is a parameter change. What kind of changes in the control action should be made? There are various choices. Once again, we are going to discuss that later. The chapter on control system design is typically what looks at this. So feedback will almost invariably be used in regulator type systems. There is hardly any regulator type system which you will find which does not have some feedback. In the final analysis, some human feedback, some overall supervisory feedback will always be there. In the case of the rocket launch or the satellite launch also, there are so many things that can happen over which you have no control. The weather, as the rocket ascends, the airflow, the density of air, quality of fuel, variations in it. One does not. Modeling a rocket motion is not that simple. One has to make approximations. So we really don't know 100% exactly what is going to happen, so that it will happen. So feedback is used there also. At the same time, in that application, one does do some pre-calculations. No system is designed without any pre-calculations. And even the feedback is designed, is calculated. So it's not that you can take anything and not know anything about it and use feedback to control it. You may succeed in doing something, but there is no guarantee that you will do a good job. So pre-calculations or pre-programmed action is useful, important, but at the same time, use of feedback is also very important and necessary. So this is about one class of systems called regulators or regulator type systems. Let us now look at a different kind or class of control systems or control actions. And I'll go back to an earlier example, namely steering. Steering a bicycle or a scooter or a motor car or an aircraft. Now when you want to go from one place to another and you want to ride your bicycle, is there anything like a regulator kind of action? Is there anything that you want to keep constant? It should not change. Maybe of course you would like to bicycle or pedal at a constant speed, but no, that's not the main problem or the main point of what you want to do. You want to start at a particular place and you want to reach another place, and there is a road or some pathway which you have to follow. Similarly, when you take a ride on your scooter or in a car, or you have an aircraft which flies from one airport to another, you know the path that you would like to follow. Of course, it can happen that you have never been that way before. The path could be new to you, but still there would be a road reasonably well defined so that you know what to do, and there would be some signs which tell you what you should do. Certainly no pilot flies an aircraft without knowing beforehand the geography, the location where is or the area over which he is going to fly, and so on. The word course is used for this. So there is a predetermined course which you are required to follow, and you get on your bicycle and get going. The road is straight, you ride straight. The road, there is a left turn to the road, you do something to the handlebars and your bicycle turns left. Of course, when it turns left, you take care that you don't hit the footpath or you don't go too far on the right side. There may be an oncoming vehicle. So you are constantly watching what's going on. But by and large, you can say that you have to follow a specific course. The course may be predetermined if it is a bicycle ride that you have been taking every day from your hostel to your department and back using a specific road, then you know it so well that maybe even in your sleep you will be able to do it. The whole course, the terrain, the road is all well known. Everything is familiar. But the course may not be predetermined. There may be sudden changes. The road is under repairs, it's closed, or left turn is no longer allowed. So you don't know beforehand what's going to happen, what path you are going to follow. The course is not completely predetermined. Yet you would like to steer your vehicle, and here by steer I mean not only direction but also control the speed. So getting onto the bicycle is one thing, of course, getting off it is another, but maintaining the speed or changing the speed depending on the terrain conditions and so on, and then keeping the orientation so as to follow the course and all of that I include that in the word steering. This is a major control job, and of course human beings are doing it day in and day out. The job is a little easier for perhaps the railway locomotive driver. Why? Because the track is already there. Unlike the road, where you have to be on the correct side of the road, not go too far to the left, too far to the right. There may be a ditch, there may be some pile of dirt and so on. The railway track is reasonably fixed, it's maintained properly. In fact, that's a big job, track maintenance. And so the locomotive driver has to simply start the locomotive, decide upon a speed depending on the speed limit, and keep going. Of course, that's not true. There are other things that he has to do. If it's a single line track, then you know what kind of problems are involved. The track condition may not be the same. There are curves, and so around curves you have to reduce the speed. There may be an upgrade or there may be a downgrade. So even there is some control action required all the time, and it's not completely predetermined, although ideally, and people are trying to have automatic trains, that is trains which will be without any driver and which will go from one place to another. But even when you have such trains, the use of feedback will be almost unavoidable, because what you knew about the track beforehand may not be actually the case. It may snow. We don't have that problem in many parts of our country, but if there is snow, what do? Even if there is a track which is completely given to you, so there is no other traffic, there is no other locomotive or train which is going to cross your path, there are no obstacles, still there could be changes like this: rain, snow, so on. So sensing, being on the lookout for what's out there and checking whether the course is correct or not, and if not, then making some changes. For an aircraft pilot, for example, this is what is absolutely necessary, because unlike the railway track, there is no track in the air. So he takes off and then he tries to set a course and he tries to stay close to that course, but then there are things that are not under his control. If it's cloudy, there are gusts of air and so on, so he deviates from the course, and then he takes corrective action from the course, from the actual course, so that the desired course is then again followed. They have landmarks and so on. So here is a different kind of control situation, which is not of the regulator type. It's not that something is to be maintained constant, temperature, pressure, speed, or what have you. It is that something called a desired behavior, position with respect to time or location on the map, let's say, as you fly the aircraft, where you should be at this moment of time roughly. That is known, and you have to try to follow that. You have to try to stick as closely as possible to that desired behavior. Such systems are called follow-up systems for an obvious reason. They have to follow something which is being specified. The main thing is that what is specified is not usually specified much beforehand. But as you go on, you are told, do this, stay close to this path or whatever. Another name for such systems, and that is the reason for that name, is the particular application that was during the Second World War, when aircraft were being used, and even rockets, as we know, were being used as a part of the war effort, and therefore you had to devise a system to gun down enemy aircraft or enemy rocket. Today, of course, one would not talk about aircrafts and rockets in the old sense of the term, but one would talk about missiles. And you have to intercept a missile. You have to first of all find out whether there is a missile in your airspace and then track it. This is again another term that is used, and then if possible intercept it. In the Second World War, it was simply a question of enemy aircraft, say, appearing on your horizon, and then you have a gun or a set of guns. So you have to keep on orienting them properly, and then at an appropriate moment take a decision to fire a shot and shoot down that aircraft. This was the time when the radar had just been introduced, so it was not really a very sophisticated kind of tracking system. Very soon, as the war effort went on, radar was developed. So you had this thing which detected the enemy aircraft even before you could see it, perhaps, or if it was cloudy and so on. And the radar would give you the position of the aircraft and also the distance of the enemy aircraft or the target. So you had this target coming to you, which you had to track with the help of the radar. But that's not all. You just did not want to track it and keep just watching it. You have to take action of firing a shell. And therefore, you have your gun, but the gun is not a small pistol or a revolver. It's a very massive thing, because the shell has to reach maybe an altitude of 2000 feet or a distance of maybe 1 kilometer or more. So it's a very massive thing, and it has to be moved. So you require mechanism to move it, because the mechanism would be an electric motor. But you have to move it, keep on moving it to follow the target, and not just wait till the target was overhead and then suddenly move the gun, because that would not be possible. It would take quite some time to move it. So in a very crude sense, the position of the gun should follow the position of the target as closely as possible. There's more to it, because it's not enough to know the position. One should anticipate what the target is going to do. But at least you should keep track of where the target is, and the gun should be oriented towards the target as closely as possible, so that eventually when you take a decision to lob a shell, there is a good chance of the target being struck. Today, of course, things have become much more sophisticated. You have missiles which are launched from Earth, which may be launched from an aircraft. All kinds of interceptions are possible. So certainly this is a very hot topic today. But this is the application that gave rise to this term, servo mechanism. Servo refers to, or comes from, a Greek word which is there in the English word servant. A slave, essentially somebody who follows your instructions, does anything and everything that you tell him or her. And mechanism, because obviously there was a gun which was to be moved, which required a mechanism, electric power or motor, and ways to control the motor. Like the aircraft, there are various kinds of controls or aspects of movement of the gun. You can think of a movement in a horizontal plane, so azimuth, and then the gun has to be raised or lowered. So elevation, so azimuth movement, elevation, so azimuth control, elevation control, and things like that. Instead of a gun which is at a fixed location, you may have a gun which can be moved around. And again, instead of a gun shooting a shell at an aircraft, it could be something else, a tank, a military tank, which will fire a missile at another military tank of the enemy. So there again there are similar problems, although the guns may not be as heavy, but the added problem is that the tanks are moving. Your own tank is moving as well as the enemy tank. So this is a different kind of control problem altogether. Unlike the regulator type system, where of course there is something desired, namely temperature should remain constant at 27 degrees Celsius, or voltage should remain constant at 230 volts AC RMS. There is something desired here, but that something desired is not constant. Not only that, that something which is desired is not even known beforehand. Nobody tells you beforehand exactly how the target is going to move. Because there is a pilot there, he might make some maneuvers which are totally unexpected. It may be a new aircraft about which you don't know much. So you have to follow something which is not known to you, and yet you have to follow it as closely as possible. So this is a different kind of situation altogether. And this was of course a very important class of control systems that was studied during the Second World War. There were of course earlier applications, but they were more like the regulator type system applications. For example, steering of a ship was a major control application. It goes back to old days. Ships have been steered for a long time, but when ships became more heavier and had more powerful engines and more speed, more tonnage and so forth, the problem became more difficult, because again there is the screw or the propeller and there is the rudder on the ship which has to be moved in order to achieve a certain speed and a certain direction. So when going from one harbor to another, of course one would have a preset course, and the course would of course usually will be known beforehand. So you keep a certain bearing, keep going in a definite direction. So in that sense it was a regulator type problem. You had to just keep the ship going in a particular direction in spite of disturbances. There would be wind, there would be motion of the water, waves, turbulence, of course storms, whatnot. So in spite of that, you have to keep the ship on course. So that was almost like a regulator type system. So such control systems were studied. One of the earliest work was done for steering of a ship. Of course much earlier work was done, as you can expect, for the control of the steam engine and the James Watt governor. In fact, Maxwell, whom one knows for his contributions to electricity and magnetism, or really to the subject which is called electromagnetism, bringing the two together, also studied the action of the governor from a mathematical point of view, and found out that there were some problems or there were some defects with the governor, and then some improvement could be made. That was around 1860s. There were problems of the servo mechanism kind even at that time. They were in astronomy. In astronomy you want to look at the sky, and unfortunately the stars don't stay fixed, they keep on moving from east to west. And so you have to keep your telescope moving to follow the stars. Of course the motion of the stars is more or less known accurately. Today one would say the motion is not that of the stars but that of the earth, and the motion of the earth is known fairly accurately. There is no sudden jerk here. The earth is not going to stop suddenly. It has not stopped nor had any jerks. But still you have to move the telescope, which could be a very massive thing, to follow the movement of the stars. So it was one of the earliest of the servo mechanism applications. And one astronomer, who is called the Royal Astronomer of Great Britain by name Airy, did some study of this application. Again, it involved obviously mathematical studies because you had to move an object, so mechanics, writing down differential equations and whatnot. So in that sense, the theory of servo mechanisms is also quite old. You can say it goes back to 1860s, 1870 and so on. But the Second World War is what led to very significant increase in the amount of study, in the number of people who were studying, in the urgency of the situation and so on. So a lot of developments took place in what is called the theory of servo mechanisms. In fact, there are books with that title, Theory of Servo Mechanisms, rather than Theory of Feedback Control Systems. And this continues to be one very important application. Servo mechanisms, follow-up systems, or tracking systems. You can use any one of these names so long as the idea is clear. There is some desired behavior, the angular position of the gun should be as close as possible to what is desired, the angular position of the target. Interestingly, there was a development before the Second World War, which in a way can be looked upon as a follow-up control system. This was a different kind of application or development. In fact, it did not really look like a control situation at all. And perhaps it is not. Looking back, one can see that what is involved is not really control action, but something quite different. In the USA, in the United States of America, there is a big telephone system in operation known as the Bell system. The Bell Telephone Laboratories, which till recently were one single entity and one heard quite a lot about it, they had the telephone network going across the entire United States. Now at that time, now this is the early 30s or late 20s, the equipment was of a certain kind. Today things have changed drastically. There were no satellites at that time. There was no satellite communication. There were no microwave towers. All communication was through cables. Because there could be wireless transmission, but that wireless transmission was not reliable, was not cheap enough, and it was not being used on a commercial basis. So the telephone system was through cables. Now you speak into a phone in New York and you want to be heard, let's say in Chicago or in San Francisco. Now if you think of it as just one wire running between New York and San Francisco, then obviously you will not be heard in San Francisco. In between, amplifiers are required. Otherwise the signal, if you think of a direct transmission, will be just too weak. So you have hops or stages, maybe every 100 miles or every 200 miles, you amplify the signal and then send it out again to the next hop. So this requires a large number of amplifiers put up all over the country at places which may be not so easily accessed. After all, the whole terrain is to be covered, or a lot of it is to be covered. So the amplifier could be at a remote place. Now what if something goes wrong with that amplifier? Eventually one will have to replace it. Now when you replace one amplifier by another, how do you know that you have replaced the original amplifier by another exactly like it? One of the aspects, as you know, as electrical engineers who have looked at electronic circuits, is what is called the gain of the amplifier. The amplifier amplifies the signal maybe by 100, by a factor of 100, or by a factor of 1000, from a particular voltage level to another voltage level, and so on. Now this gain of the amplifier, as you know from your electronic circuits study, those of you who have studied electronic circuits, the gain of the amplifier is not constant, it can vary over frequency. And at that time the amplifiers used vacuum tubes, no transistors had been invented by that time. So it was dependent on a number of things. Let's say replacing a whole amplifier by another would be a problem, but an engineer would go to a particular repeater station, as it is called, open up a particular amplifier, and he may find that a particular tube or valve is not functioning. So what do? We do exactly the same kind of thing today. Take out that thing which is not functioning and replace it by another. So if you see that a valve is not functioning, let's say the heater light is not on, so it's gone bad, you take it out and replace an equivalent valve or tube. Now the trouble is, the equivalent valve or tube that you have replaced the original with is not absolutely identical with the original tube. So with the replaced tube, the amplifier gain may undergo a small change. This is only one example of a vacuum tube going bad or losing its power, so to speak, so requiring a change. Because of the climatic conditions, the gain could vary and things like that. So what you needed is an amplifier whose gain will remain nearly constant, irrespective of some of these influences, environmental influences, maybe irrespective of the tube, the exact vacuum tube that you used. The vacuum tube was associated with some parameters. One of them was called the mu of the vacuum tube, or the gain of the amplifier of the vacuum tube, and so on. So you wanted to design an amplifier which would not be so sensitive to your parameter mu. Even if mu changed by, say, a factor of 2, it may not change by that much, but let's say it changed by a factor of 2 or even 20%, your gain will not change by 20%, but your gain will change by a much smaller amount. If possible, of course, no change. Gain should be absolutely constant, irrespective of the value of the mu, or irrespective of the tube that you are using or changes in its characteristics. So you have to reduce the sensitivity of the gain of the amplifier to parameter variations. Make the amplifier gain less sensitive to parameter variations. And one of the engineers of the Bell Labs, by name Harold Black, thought of an idea of doing it. And this idea was that of using feedback. I'm sure he got this idea from a control system application, typically the application of steering that I've been talking about. But this was the first time that feedback was used, not for a control application, but for a different application altogether.